I am starting. That's kind of our code for it's time for you to stop talking. All kinds of seats, but if you're just walking in, just walk around till you find one. Anybody still needs a pass out, there's a couple up front if you want to grab one. Okay? There's a couple of blank slides that are inserted just to pause, ask if you guys have any questions you want to ask here. But I just want to go through some of these fairly basic questions we've got here. Question number one is kind of a timely article. It's about cyberbullying. And as you read through this, you're going to see there's a sample of men, a sample of women, and each of them have responded in terms of whether they've been victims of bullying or not. All right? And what we've got is we've just got the sample sizes here. This is N sub 1. This is N sub 2. And this 20% that they talk about the females right here, all right, is, you can see how many of them reported they had been bullying just by figuring out what P hat is. That's a good question, but that's not the question we've asked. What we're interested in is testing the proportion men versus women, two independent samples comparing two population proportions, all right? So the hypotheses here are going to be P1 equals P2. And I have to be careful here. I'm going to put this in here, but I've got to make sure that I get the right direction in here. P1 is males, all right? And we're asking to see if the results indicate that females will be more cyberbullied than males, all right? So that particular word right there drives the direction of our alternative hypothesis, okay? And I think what's going to happen immediately is we jump you right to the test statistic, right to the p-value, right into some true-false test. We could ask you to calculate that particular test statistic and p-value, but this is a question about, just to understand some of the basic elements, true or false about this particular situation. The results are statistically significant at the 5% level. That's true if the p-value is less than or equal to 5%. That's not true here. P-value here is 0.055, so this is just a real easy one to start with. That's false. At the 5% level, the cyberbullying rate for high school females does not appear to be higher than that for males. That's a conclusion. It's a conclusion with respect to this p-value, which led to failure to reject the null hypothesis. And that particular conclusion right there reflects those populations, reflects those parameters, proportions. So that's true. Okay? I'm going to find a way to trip on one of those before this evening's over with. Okay, so you can leave yours in the middle, and I'll see if I can trip on that first, all right? All right. Number two, the probability that the null hypothesis is true is estimated to be 5.5%. What we've done there is we've put an interpretation on the p-value. The p-value is 0.055, all right? And what we've done right there is we said, well, the probability is true is about 5.5%. That's not low enough. That seems like a reasonable statement about a p-value, but it happens to be one that's false. And I need you to know exactly what a p-value is. You need to write this down if it's not immediate, that it's right there that the p-value is the probability of what you observe or anything more extreme, assuming the null hypothesis is true. And that's the only thing a p-value is. And I could write it like this, all right? This particular test is one-sided to the left, all right? I think, all right? So what we've got right here is the p-value equals the probability of what we observed, or anything less than that, assuming 8 sub 0 is true. And that's the only thing a p-value is. if this study were repeated many times, time after time after time. Okay. When I say this study, I mean this study with these sample sizes. There's a 5.5 chance that the cyberbullying rate for high school females is higher than for high school males. Almost true. The only thing that we need to put in here to make it true is if H sub 0 is true. If I add in that particular assumption, that the null hypothesis is true, that particular statement there is a statement that makes sense. But the way it stands, it's false. Cyberbullying rate for the sampled high school males was 1.6 standard deviations below the rate for females. All right, that's true. Here's an interesting one. One condition for the test to be valid is that the response for each of the populations is normal. The response for the populations are either I have been bullied or I have not been bullied. That is discrete. Since it's discrete, those particular discrete distributions are on bars or on spikes. That's not normal. So this particular problem, this particular example is false. Problem number 2. Read this problem. You're going to see, I think, 40 apartments here chosen at random. That's in. What they're worried about is the air conditioner, all right? So they're taking a sample and they're getting the temperatures before and after the air conditioners go on, all right? And what they want to do is they want to use a 90% confidence interval. And let me read this and make sure we've got all this. Okay. After installing, they received several complaints that the air conditioners didn't seem to be working. They decided to run a test to see if the unit significantly changed the temperature of the room. Here's our sample size right here. Okay. So they record the temperature in the center of the room, they turn on the air conditioner, and they come back a few hours later, get the temperature again. So what they've got within each room is a temperature before and a temperature after. What we've got to is that particular element there, which is change. And the statistic that measures that, of course, is D bar. And what you're going to get in the next particular array is some different statistics here, and what you're supposed to calculate is the 99% confidence interval. They give you this particular set of statistics here. I put part of it in red just to emphasize that once we get the statistics around the change, the statistics before and after don't really participate. Okay? They're not really very useful. The parts in red about change are the thing that drive the particular confidence interval here. Go to your yellow card if you want, but what you're going to do is you're going to take the mean, plus and minus, oh, I need to think about this for a second. N is equal to, I said, 40, right? So the multiplier here, notice I've got standard deviations here. Standard deviations are going to make this a T multiplier here, T star, and the degrees of freedom are going to be 39. All right? And when I go to the card to look up 39, it's not going to be there. It's between 30 and 40. So what we've asked you to do is take the smaller one and be a little bit more conservative. Remember? Right? And right here, all we have to put in right here is the standard error. Now, the standard error is the standard deviation divided by the square root of n, but that particular thing is loaded right there. All right. And the multiplier that we're going to pick off the table at 30 is going to be this number right here, using n is equal to, using degree of freedom equal 30. can't get to 40, can't get to 39, right? And so this particular idea, when you multiply those together, well, I didn't write that number down. I do have the interval, right, is 0.1648 to 1.865. And there's your answer. Okay? Questions? Anything else that I could answer now? Yeah, did you have a question?
I don't know. When I calculated that, I got a minus 0.165.
Did anybody calculate that? That looks like a mistake I would make. I got 2 votes right there. Maybe I forgot to write it down. Do I have 3 votes? This looks like a mistake. Good? Okay. You're okay. Minus. All right. I need you to stop talking now. General questions. Okay, let's go on to this one. Jane is curious about the factors that influence paper grading by professors. She has a hunch that papers that are typed are graded higher. That word higher is going to drive the alternative hypothesis than papers that are handwritten. To test her hunch, she conducts a study. She's got 43 freshman students currently taking English. 20 of them typed their latest paper. 20 handwrote their latest paper. 23 typed their paper. All were submitted to one professor who teaches English. Jane obtained the scores from the professor in terms of whether, and entered the data in the SPSS, alpha is 5%, all right? And just for the moment, I'm going to ask this other question in a second. Just assume the conditions are okay. Just for a moment. That's going to get into the very last question that I'm going to ask you about in a second. So here we're talking about higher grades. I reminded myself right here to see the next slide because I know I've got 2 independent samples, but I don't know exactly the SPSS output in terms of what was written in terms of handwritten or typed. So let me look ahead just for a second. The typed is number 2, and that kind of makes sense because that one's higher. Okay? Now let me go back and just make sure I use the 1s and 2s correctly. This is going to be mu sub 1 less than mu sub 2. Okay? Mu sub 2 dominates. And what we've asked you to do right here is, no, I'm sorry, I'm going to ask that later. I don't need this right now. What assumption allows us to pool? And the quickest way to write, who said that? You said that. Somebody said that. The variances are equal. Thank you. The quickest way to wrap up full credit for this is to write the variances are equal. You can also write the standard deviations are equal. Sigma 1 is equal to sigma 2. You can also just say the variances of the 2 populations are equal. Okay? But the next question here is, how do you show that? And there are 3 ways to get there, and I want to make sure you've got these. Way number 1 is just the general idea that the two sample standard deviations are similar, are pretty close. Second way we could do this is side by side box plots. What we're doing is we're comparing variability. We look at the variability of the IQRs, the length of the boxes. We also look at the whiskers, make sure they're basically the same. And of course, the last way, we love this way, is Levine's test. For Levine's test, you literally test this hypothesis right here. And after this, you can write wanting to, in parentheses, except 8 sub 0. And you want its p-value to be really big. We set alpha usually at 10%. We want that p-value to be much bigger than 10%. Not a doubt that we can make that assumption. Gives you the test statistic right here. It gives you the p-value right here. I can't remember this. Did we say alpha of 5% in the setup? All right. And what you've got to do is pick a conclusion that kind of reflects what we should be telling students as a result of this study. All right. We reject the null hypothesis. There is a difference. Okay. It turns out that typing is beneficial, and if you read the last two, it doesn't matter. That's when you the words around accepting the null hypothesis or failing to reject the null hypothesis, right? So the last two aren't contenders. So what you've got to do is you're going to have to pick the one of the top, all right, one of the top two. They would want to type their paper because the study supports that type papers get higher grades. On average, we're talking about averages, so this is your better choice there. Question number D. This is kind of a so-so study. Notice we ask you just to kind of accept the fact that some assumptions were true. Any criticisms about this study? What would you say here? Hold up your hand if you want to make a, yeah.
Confounding variables.
Confounding variables. They could be influencing things, yes.
Assumption of causation.
Pardon?
The assumption of causation.
The assumption of causation. I like that answer too. Not the one I'm looking for yet. Sample size is less than 30 is, yeah, we haven't checked whether it was normal, okay? So you need to look at that. I'm sorry, I can't hear you. You need to say a little. I can't hear you. I'm partially deaf. I'm wearing hearing aids. I still can't, what? Not independent enough? Is that? I kind of got that out of. Yeah, that's getting in. Yeah, I'm sorry, I didn't hear you very well. That's really my fault. Yes. Say that again. There's only one teacher. Does this look like it's representative of anybody? All right, just that one teacher, right? Now, all those comments were good answers, but this is the one that I think kind of stands out, is that particular sample is, when you think of the population that's representative of, it's very small, all right? Very small. So this is one of those particular examples where you would say thank you, but it wouldn't really, you might believe this, but not as a result of this particular study. Question over here? All those answers were good answers. IQ scores. Suppose you are interested in estimating the difference, average IQ for females and males. All right? So you've got, oh, this didn't come through, you've got mu sub 1 representing the population average, all right, for females, and mu sub 2 equal the population average for male students. You took a random sample of 100 that were 50-50. That's not bad. This says that because of some reason you've used the unpooled procedure, maybe you looked at variances and they seem a little shaky, and what you've got is a 95% confidence interval that goes from -1 to 11. We good? Okay. True or false? Who said that? Shh. The average IQ score for the sample females was 5 points higher than the sample for the male students. Notice right here, what you've got in this particular middle of this table is you've literally got this difference right here. In the middle of that table, that's equal to, and what you have to do is really just add these together, divide by 2, and that answer is 5. That's the middle of the table. The average IQ for the females was 5 points higher than the average for the sampled, the average for the females was 5 points higher than the average for the males. All right? True. With 95% confidence, we would estimate the difference of these averages to be someplace between -1 and 11. That's not only true, that's a really good interpretation of the confidence interval. Okay? Confidence interval, we're 95% confident that the difference, mu1 minus mu2, is in that interval. The next one's a little bit more difficult. The pool procedure, now this is unpooled. This is the unpooled right here. If the pool procedure were used, you would get a narrower interval as the t-star value would be smaller. Remember this, pooled makes the degree of freedom larger. That's one reason we like it. Get narrower limits, get more powerful hypotheses. When the degrees of freedom get larger, the t-star gets smaller. And all you have to do to see this is go to table A2 and watch what happens as the sample size goes up toward infinity. In fact, as it goes up toward infinity, the t-star approaches the normal 0, 1, 1.96. All right, so this gets smaller, and when that gets smaller, the interval becomes narrower. It's true. But if we were testing it at the 1% level, all right, is it rejected or not? Now let's go back to the thing we just had just for a second, okay? Look at this particular interval right here. If I were testing this versus an alternative, mu1 is not equal to mu2, it's really a pretty simple comparison right here because all I have to do is recognize that 0 is in that interval. See that? And if 0 is in that interval, that means we would fail to reject the null hypothesis. And notice here, what I'm talking about is a 95% interval against an alpha of 5%. It's got to be two-sided to make these things work. But what we ask in this next question is, what happens if we do it at 1%. So if this is our level of significance right here, what we have to think about is a 99% confidence interval. You know what the confidence interval is for 95%. It contains 0. That was important. What's going to happen to the 95%? The 99%? Is it going to get wider or is it going to get narrower? And it's going to get wider, right. Couple of reasons to think about that. At 99%, you've only got like 1% chance of being wrong. That better make it wider, all right? 99%, that multiplier is going to get higher. It pushes it out, all right? So because of that, this particular interval is wider and still contains 0. And if it still contains 0, that takes you right back to where you were before. Before we get into Big John's ropes, any questions in general? Now, you guys sit there. As soon as this is over with, 30 of you will be up there asking me questions. Does anybody want to step up now and ask me a question? Oh, I see somebody. Yes. I'm going to get over here closer so I can hear you. Yes.
If that were on an exam, like, would you need to explain that the 99% confidence interval corresponds to the 1%?
No, no. We see that you're walking the right step to get there. What you've done right there, as you said, the 99% interval, you know the logic. Now you just have to tie it together. Good question. Other questions? Yes?
Okay, so for question 3, when to know if these variances are equal or not, you can look at side-by-side box plots. If you had a side-by-side box plot on the test, what exactly would I look at to make sure?
The question is, what do you look at side-by-side box plots to determine whether you can pool, whether the variances are the same? I need to have you guys kind of stop talking a little bit. Thank you. When you look at side-by-side box plots, you look at the length of the box, all right? That's the IQR, and the length of the IQR should be kind of similar, all right? One shouldn't be time and a half as the other one. I'll get to your hand as soon as I'm done here, okay? I promise, okay? So you've got these boxes, and they should be about the same length. And then you look at the whiskers, all right? If one whisker is much larger than another whisker, like the right whisker compared to the right whisker for the next one, that's a signal that something is not similar. So you look at the comparability of the whiskers, the comparability of the boxes, and they should be approximately the same. Okay? What's that? The means don't have to be similar. That line in the middle, the means don't have to be similar at all. You're just asking a question about the variability. Are you good with that? Did you have a question in the back?
Based on this one interval for that one sample, that the population was in there. I thought it had to be from, you have to take multiple samples.
No, that looks like the one particular confidence interval there represents one sample representative enough of that population, and you can make statements about one sample reflecting to the population. And with 0 being in there, that does prevent you from rejecting the null hypothesis. Okay?
When you're looking at variances and you say they need to be approximately the same, how close is
All right, good question here. When you look at variances, when you look at standard deviations, I've been a little bit vague in saying they have to be reasonably close, all right? They have to be pretty close. Now, That's a hard question because there's a gray zone in there. And if I give you these two variances, 2.1 and 2.4, they seem pretty close. If I give you these two variances, 2.1 and 11.7, those seem really, all right? What I'm doing is I'm giving you examples of ones that are obviously close or obviously really far apart. We won't mess with you in the gray zone, okay? One good way to answer the question in the gray zone is with Levine's, because if that p-value is greater than 0.10, you're okay. But in terms of those general comparisons, we're either going to be really different or really similar. We're not going to put you in something that's debatable. Other questions before I do I think the last problem? Okay. Let's be quiet a little bit more. Here's Big John Ropes. The rope company has been in the production for almost 75 years. It keeps extensive records in terms of the quality of their various ropes. The half-inch rope is known to have a true mean breaking strength of 865 pounds, and what you've just learned is that is the value for mu. They've looked at so much data for this particular kind of rope they make, they think of that as a parameter because they've tested it thousands and thousands of times. And that standard deviation right there of 9, all right, is sigma. They've got that from just an incredible amount of data. So what we've done in this particular setup right now is we bring you data that has that mu and that standard deviation, all right? But it also tells you it's positively skewed. What that means is some ropes have extremely large breaking strengths. Does that make sense? Every once in a while they make a rope so well that it takes an incredible amount of force to snap it. So what you've got right here is you've got a distribution that's positively skewed. It looks like that. You have a very few high outliers. What you do know is it's not normal. Here's kind of the setup. A summer intern is unaware of this. He's got some time on his hand, so he decides to find out the breaking strength of this rope by testing a random sample of 64. The first thing that pops in your mind with 64 is the word large or the word small. That's large. That's way past 30. And the good thing about large samples is that the X bars that come from them become normal. Not the original data. The original data is still skewed. But what we've set up now is this idea that sample size of 64, that's going to create normality because of the central limit theorem. And what we're going to get are these X bars, sample after sample, size n equals 64. Those become approximately normal, right? And the normality you've got right here, I didn't give myself enough space to write it. The normality you've got is centered around this, and the standard deviation is this. And this particular normality right here, we can say, thank you, central limit theorem. All right? And this is equal to normal. All right? The mean is this number right here. And the standard deviation is now 9 divided by the square root of 64. Hang on. Hope I did this okay. And that number right there, 9 divided by 8, is 1.125. So what you've got now And this is exactly like the kind of problem you had on exam 1, except you need to think of this distribution of the x bars. All right? And what we're asked here, we've got a center around 863. We're asking the probability that his x bar is greater than or equal to 860. We're asked for this area right here. We had a similar problem like this in exam 1, except it was about p hat. Okay? You've got sampling distributions of p hat, sampling distributions of x bar. Right? So all we've really got to do now is take this particular value right here and convert it to a z. Minus the mean divided by the standard deviation. And the z value here is minus 2.67. And the next step, of course, is the probability that z is greater than or equal to minus 2.67. You go right to the table and look that up, and that particular area is 0.9962.
I used the t-test, and I got the same result.
He used the t-test. Why did you use the t-test? I'm going to yell at you in a second.
Because there's mean.
Huh? No, that's not a good reason because it's mean. When do you use the t?
Hypothesis only?
No, you use a t when you see s. Here you've got sigma. See that? You don't get that s from a sample. And it's when you get the s from a sample that takes you into a t. So this particular problem right here, you get to use normality 0, 1.
Okay, got it. Thank you.
Other questions before I do the last one? Yes?
Since you're given sigma, why do you need to use 9 over?
Because the question was, if you knew sigma, would you guys hold it down, please? If you knew sigma, why did you use sigma over the square root of n? It's still the distribution of the x bars. The x bars are normal when the n is big, and the mean of the x bars is mu, and the standard deviation of the x bars become closer together because they're centered around mu. Their standard deviation is the sigma divided by the square root of n. Yes?
So does the amount of skewness not affect the probability that it's greater?
No, it doesn't at all because we're talking about a problem about x bars. And when that n got to be 64, you got to normality. Okay, that was a huge sample size. So the skewness of the original distribution doesn't become part of the issue anymore.
So the question were to say that it's approximately normal, then you still use the same formula?
Yeah. You could say it's at 64, I think it's to normality. Technically, you could say it's approximately normal, but you use normality. Okay? If it's n is equal to 32, I'm not going to talk like that. Would you guys hold it down?
How do you know when to use sigma and not s?
The question is, when do you know when do you use sigma and not s? You use sigma when the problem gives you that you know so much about the population, thousands and thousands of ropes have been tested, and after all of that extensive records, you can see right there that that's mu and that's sigma. S has to come from a sample. And as soon as you just get that lonely S from one and only sample, that's what takes you to T. Okay? Other questions? You guys are a rowdy crowd. Other questions? I've only got one more example. Way over there. Yes. I gotta walk over the little ways, otherwise I won't hear you. Yes.
If s divided by square root of n is the standard error, then what is sigma divided by square root of n? Does that tell us something else?
Okay. Here is the question. Okay, this would be, you guys are going to be out of here in 9 minutes, maybe 11. Okay, so kind of knock it off. Okay, help me out, make sure I got that right. S divided by the square root of n is the standard error, right? That estimates sigma divided by the square root of n. The question was, what is sigma divided by the square root of n? And that answer is simply the standard deviation of the x bars. Standard deviation of the x bars is sigma divided by square root of n. And if you don't know that and you have to use sigma, s, then that's when it becomes an estimate of that, the standard error. Got it? One more maybe before I work the very last one? Up. Oh, not you.
Are we supposed to be calculating a z statistic or a t statistic?
Right here you calculated a z. And it's z because you know that is sigma. Okay? And once you get it here as a z, you're going to use table A.1. Okay, noisy crowd. Any more questions before I do the last one and let you go? This would be a good time to shut up. Any more questions? I know you're going to bolt after we do the... And after you leave, I'll stay up here for as long as you want asking questions or answering any questions. Okay, let's do the last one. Okay, you will see a question like this. What I'm asking you to do is to define a parameter. When you define a parameter, make sure you identify the population and make sure you identify what's being measured. So this particular mu right here is the population mean for the breaking strength for all 1/4 inch rope, you ready for this? Made with that new fiber. Okay, now make sure I got all the elements in there. I nailed it down to the population, didn't I? All 1/4 inch rope made with that new fiber. And I told what continuous variable was being measured. And that's the breaking strength. That's when the rope snaps. Okay, I made sure it was a population mean. We good there? Population mean of the breaking strength of, and I always capitalize the word all. Just so the GSIs that are grading your exam, population of all the 1/4 inch rope made with the new fiber. Okay? The distribution that's going to determine this, notice what it gave you right here is this guy, which came from this one and only sample. That makes this distribution, because it's a t, it has to be, because it's the s from a sample, this is a t distribution with degrees of freedom of 19. We good? Now, the next part I think is interesting because it talks about a couple of basic themes here. First of all, here's what we've got to test. We've got to test this hypothesis right here versus a hypothesis that goes to the right. It's one-sided to the right. Now, at this point, I want you to pause. And I just want you to take a look at that particular x bar. Is the x bar to the right of that null value? like you kind of want it to be? And the answer is no. Right there, that moment of thought tells you that something's kind of messed up here. Something's kind of different right here. All right? It gives you the test statistic right here. The test statistic was t, and it's negative. And it's negative because this particular test statistic was equal to the x bar, which was this number, minus this number, divided by the standard error. And notice right here, this particular difference became negative. And right there, what you wanted to happen with this new fabric, this new fiber, is you wanted that to enhance the breaking strength, but it's not even up to where the null value. All right? So something's not exactly right, and you can see that by sketching the p-value. And I'm not sure if I've got a blank slide on the other side. We do. It's going to look like this. All right? The p-value, I want you to draw a t in here. Make sure you're crystal clear about what the distribution is, what the x-axis is here. The middle is 0, but right here is your test statistic. All right? And now let's pause and think about the p-value. The p-value is the probability of what you observe. That's this value right here. Anything more extreme to the right, so we go in this direction right here. So this p-value is literally this area right here. And that area right there, my answer for the p-value here is all I have to recognize is the p-value is greater than 0.5. Is that general enough? The p-value is huge. This p-value is such that there's no way we'll reject h sub 0 because the p-value is huge. Now, that's an important example for two reasons. Number one is the way I wanted you to pause there and recognize it. Don't rush through the analysis. You've got to kind of think it through a step at a time. Number two, you can see that particular huge p-value right there. All right? Hang on, you're almost out of here. Have you done something in lab that had this kind of situation and SPSS gave you a p-value? Remember that? Now let me go over that just to make sure. You're almost out of here. What SPSS does, they don't know, SPSS doesn't know whether you're one-sided or two-sided. So in this particular situation, what SPSS would have done is not only given you this area right here, it always gives you a two-sided area. All right? What you really want is this area right there. So you would take the SPSS p-value, divide it by 2, that gives you one side, but it just gives you that side, and then you have to subtract from 1. I just think a good answer is the p-value greater than 0.5, and you're done. There's no reason to find out any more. That's it. I'm up here for more questions.
Okay, so 2 questions. One, I know